Yeah, so it's time to start. This is unusual time and unusual special seminar. So today's speaker is Dr. Elisa Ferreira from Cavalli IKMU. She will talk about CMB tension and implication for inflation. Okay.
Thank you so much. Thank you so much for the opportunity of giving a second talk. I really wanted to talk about this because as we were talking, this is a hot topic, and I think there will be a lot of papers and discussions about this in the next few months that you're going to see in the literature. So this is a very hot topic. But most of all, I found this really interesting, both for theorists and for people that do observations. So I found this really, really interesting thing that we found and other people found at the same time. And it has huge implications for how well we can constrain our models of cosmology. So before I start, I'm going to say that I'm more or less on the same topic as before, that I love how you put it, like we get more precision, but we get less precise because there's so much complication that comes with this more precise data set, with this more precise observations and more complex observations. So I think we're not ever, again, in the time that I measure this supernova, I measure this BAO, I combine everything is great, I have more constraining power. I honestly don't think we're there. I think every data set has its complexity, and using all of them is becoming more and more complicated. And I hope that at the end of this talk, you're convinced of that. So this talk is based on those two papers. This one just came out, this one, it should be out soon, really. I was just finalizing the draft today, and it should be out this week. That are exactly the same title as the presentation. Okay, so in this talk, I'm going to focus more on the consequences of this tension that I call in the early universe, but I'm going to talk a little bit in the end about other consequences. So let's talk about the early universe, because this is something we thought we knew how to measure really precisely. So one of the explanation, the current paradigm that we have for the explanation of the dynamics of the early universe, it is a theory of inflation. It is not the only theory, but it is the current paradigm for the best explanation for what happened in the beginning of the universe. And it is this period of accelerated expansion in the early universe. One of the most beautiful things about inflation is that it was a prediction and not a postdiction. So someone predicted that the perturbations or the primordial density fluctuations coming from the inflations would be nearly Gaussian, adiabatic, and described by a spectrum that is almost scale invariant. So almost does not depend on K. This was predicted, and then this was finally measured by the CMB, which is pretty cool, right? Knowing something from so early in the universe and using theory to predict that and then measure really well. So this was confirmed by observations from the CMB and large-scale structure. In the case of a scale invariant spectrum was completely excluded. So now we know that if we parameterize the power spectrum from the early universe in this way, so we have AS, which is the amplitude, K to the NS minus 1. So I said it is closest to scale invariant. So this NS should be smaller than 1. This is the prediction of inflation. And this is the way we parameterize the power spectrum. And this is exactly what we measure. And this is here in a reconstruction of the power spectrum. So we see something quite scale invariant here on the scales that we measure from the CMB. And having this, measuring the value of NS and AS, as we do in cosmology with the CMB, it is a great discriminator of inflationary models. So you know you cannot have an inflationary model that gives you a blue bar spectrum or something like this. So when we measure this back in the Planck time, this was great. We could actually pinpoint a little bit better what are the possible models of inflation that are valid. And this is what is shown in this plot. So here we have this NS, the spectral tilt. Here we have the tensor to scalar ratio, which is the ratio between gravitational waves divided by those scalar fluctuations that we just talked about, that we predicted. Here, those contours. So remember those type of contours here, this ellipses are the 1 sigma and 2 sigma points data that we measure. So here we have those ellipses for different models, for different data sets, right? So here, for example, is Planck alone, which is just CMB. Here is CMB2. Here is CMB plus BAO, which is large case structure, which is late times. And we see here the contours. And we see that not all models of inflation, here we have many different models of inflation, are good measure, are well determined by the data. You see here, for example, this is excluded by the data. So that's why we say that measuring NS is a great discriminator of inflationary models. And what did we learn from Planck in 2018 when we had the final result?
26
Yeah.
will be up to 2 or 3 sigma.
Which one? Which one?
So the bottom one, what is that data?
This one.
Yeah, what is that model?
This model is low scale.
Low scale, I see.
Yes, it's Suzy. And then we have this one, 5 to the 2/3. And 2 points here is because you are assuming how long did it take inflation to last? Or for the experts, how many foldings? From 50 to 60. So the inflation was this long or this long? So there is an uncertainty. So they put here as this.
So 5 to the forward, so in the most naive case, it is excluded up to 2 sigma or
Yeah.
something.
And then if you read this, you're going to see that the viable models after all of this, it will be something like the Starobinsky model of inflation, Higgs inflation, alpha tractors, and in general, a preference for inflationary models with exponential expansion.
In your previous page,
Yes.
you mentioned the spectral index.
Yeah.
So, and the confirmed by large scale structure.
Yeah.
So if it were exactly NS equal to were exactly 1.
Yeah.
Then what would be the large scale structure look like? It should be in any scale the same structure.
Exactly. There's no dependence on scale, right?
And
And that is
now,
not what, that is excluded with a lot of sigma. Yeah. So as you can see here, 1 is excluded with many sigma.
but this is not the large scale structure data.
Oh, this is CMB and large scale structure. Yeah.
So how can I read the large scale? Large scale means order of some few megaparsec or something.
Yeah, so we're taking the entire CMB map,
Mhm.
which is the entire sky,
Mhm.
which has all the possible structures in the universe. And we're taking 2-point correlation functions in the temperature of CMB. So that is large scale
That's what
structure.
you mean, large scale.
Yes, yes.
structure.
Yeah.
I'm not there closer, so I'm not.
Or you can also combine with BAO data, which again, it is a huge catalog of galaxies, gigaparsec distance, and I'm taking 2-point correlation functions in different distances in this huge map. Yeah.
Separately, also these data excluded.
Yes, separately as well. So one
This
thing,
data is excluded.
so scale invariance is excluded with many sigma by any data separately. BAO data does not measure NS directly, So you usually combine with CMB data because CMB data really gives you all the cosmological parameters. BAO, we're going to talk about what BAO fixes here, how BAO helps this. Yeah. But this was the status that we had until this year. We were actually saying we know AS really well with a lot of precision, NS really well with a lot of precision. And then we know what are the classes of general models of inflation that are preferred and which ones are excluded. So this is what we thought we knew, and Planck is an amazing, beautiful data. So we trust this well. So then we were like, what is the goal for the future? Oh, primordial gravitational waves, right? We need to settle that R value that we saw in the previous slide. So you can see that this is not well constrained. So how can I distinguish between all of those models that are left? We need to measure other characteristics like the gravitational waves, non-Gaussianities. So all of this is assuming Gaussianity, but let's do the 3-point correlation function, 4-point correlation function. Features in the Power spectrum, maybe tiny fluctuations in the Power spectrum, or even new phenomenology, like we're now saying that parity violation might be something that our universe has. So, and that's the main goal of the next generation of CMB experiments, right? Lightbird, Simon's Observatory, CMBS4, they are here to probe these extra quantities because we already nailed down NS and AS. But in a big but, in 2025, NS is back to the light as something that we maybe don't know exactly what its value. And here I give the conclusion of the talk if you get too tired after I explain everything. So basically what we're finding is that there is a discrepancy between CMB data, current ground-based CMB data, and BAO data from DESI, which is also new from last year and this year, what we call the BAO-CMB tension. And you can see here in these quantities, omega matter and RDH are two quantities measured by BAO directly. And we see here that ACT, which is a CMB experiment, measures this like this, and X plus DESI or DESI alone measures something very shifted from it. So we can see here in omega matter as well. Two experiments that are measuring the same quantity, and they have a very good precision, are measuring those quantities, very different values for it.
So ACT is measuring CMB.
CMB.
How about the DESI? They are measuring
Large scale structure, galaxies. Galaxies, yeah. 2-point correlation functions of galaxies. Still large scale, but late time, yeah. And then we see this discrepancy. And yeah, and I'm going to say that in detail. I'm just giving a little bit of. And this, for example, this type of uncertainty shows up in an S as well, where we see a shift of something like 3.34 sigma. And again, let me remind you, think that this is a Gaussian. Sigma, it is this distance here. So this is how precise is my measurement. So this means that I'm 3 sigma away from the value, one value of each other.
what is the R sub T?
Oh, RDH. So I'm going to talk about that.
Oh.
So this is just like a, and this will have large consequences for inflation. So that's what we're going to talk today about, how this data that should be here to make those error bars smaller and nail down things a little bit better actually brought us another tension. If you don't like the tension or tension discrepancy, okay, so let's unpack this slowly. So let's first talk about what those things measure, so we really understand what is happening. So we are now currently in an amazing time in observations, and if you were in my talk on Friday, maybe you already know that I'm very excited for the future. So all of those things are about to happen, are either happening, which is what we call stage 3, or about to happen, which what we call stage 4 observations. So for example, here we have DESI, but we also have LSST, all of those happening, ACT-SPT happening, but we have a lot to happen in the future. We usually say that forget those dates, we are all shifted because of the pandemic. But we usually say that this was the quiet time of cosmology. So everything we had until today, with all these discoveries you hear every day about gravitational wave, this is the quiet times. We're going to have a huge amount of data in the future. Huge, huge, something like we never had in the history of cosmology. So that's very exciting.
So the line is shifted because of the COVID.
COVID, yeah. Yeah. So it shifted here, I think. And all of those things were shifted here. So everything is shifted here. Yeah, everybody got delayed. Okay, so we should wait great things about this. More data, more precision, great things. So the ones of the time now, the ones that are already here are DESI and the ground-based CMB experiments, ACT and SPT, right? Those are the ones of the moment, the big data sets of the moment. So let's understand what are they and what they measured. So let's first start with DESI, which is this really exciting data that we're all talking about. So what is DESI? So DESI, it is the dark energy spectroscopic instrument. So it's really measuring, getting the bunch of galaxies and quasars and getting their entire spectra. It measures a huge amount of galaxies, 40 million galaxies in different redshifts. So here we have galaxies in low redshift and then go up and until you have Lyman alpha and quasars at really high redshift. So we're measuring galaxies and the spectrum of those galaxies until redshift 2, which is something amazing. We have not done that before, right? And the amount of galaxies that we have is huge. So we're really like having the 2-point correlation functions of all of those things.
RRG, ELG, there is the
Different types of galaxy. So one is like a red galaxy, other is another type of galaxy. So those are different types of galaxies that you have in different redshifts. So they call this different tracers. So they're all galaxies, but they have different properties. And then when you analyze those, you have to know the properties of those galaxies. So the first,
they cover essentially some half of the hemisphere, or
yes, something like half of the, I think DESI is something like 30 or 40% of the sky. It is a lot. It is what we call large volume. It's really big. Yeah. There's other that are more focused. Yeah. Not DESI. DESI is really large. Yeah. It's the largest actually. So it's deep and large. That's why it's so good. Yeah. So they had the first batch of results in the DR1 in 2024, where they had the BAO results and also what they call full shape. And I talked about this a little bit on Friday. You either get the wiggles of the BAO, either you get the wiggles, which is the BAO, or you get the full shape of the power spectrum. No, it's not very important. And then there was a second batch of results, what we call the DR2 data release 2, where they only released the BAO results. I'm going to explain, don't worry. And just so you have an idea of how amazing this sample is, so this DESI DR2 sample, oh, it's here, don't worry. Yeah.
oh, I see.
Just saw it, sorry.
Okay, okay.
My bad. So this DESI DR2 sample, just so you understand, it's from 3 years of observation, and it's over 30 million galaxies, quantities we never had. Oops, and different tracers. You see like the amount of each of those. And you see that compared with DR1, it is really a big jump of the amount of galaxies. So you have a total of 2.4 times improvement in data volume in comparison to DR1. But most important for this talk, we need to understand what those DESI measure. And then we need to understand what CMB measures, and then we can understand how we compare it. So what does DESI measure? So DESI measures this feature called BAO, which is the bioacoustic oscillations of the universe. So for the students here, so when the universe was very hot and dense, everything was in a plasma of radiation and matter coupled to each other. So let's think like the photon tries to escape, but always finds a matter there, always finds a nucleus of something or a neutron or something. So we call this a plasma. And gravity wants to make this clump, right? Gravity wants to make this is matter, so this wants to clump. But then there's this pressure from radiation and baryons making, oh, no, you cannot clump. There's radiation pressure, and then it goes. And then it keeps doing this oscillation. We call this bioacoustic oscillations. And at the moment these photons, the universe is expanding and becoming cooler and cooler, at some point those photons can escape. And then it is imprinted in the structure of your universe, the size of this oscillation. And here you can see in an exaggerated way. This means that all the densities, all the galaxies of our universe have a preferred distance, which is the distance of this oscillation at the time that the photons decoupled from the plasma. So that's what we are trying to look for statistically. So we look at the whole distribution of galaxies in our universe, and we're trying to find this, because here it looks like just an arch, but this is like a sphere, right? So that's what we're trying to look for in the distribution of galaxies. It is not as beautiful like this. It is very, very faint, but we can see statistically. And that's what DESI is measuring. DESI is measuring the line of sight of this BAO feature, and also the redshift, right? So the line of sight and the redshift of this.
Right.
Sorry, the line of sight and the redshift.
I have
Yeah.
a question. The picture on the left side, does it really have a kind of a sphere and inside the cluster? And this is because of the BA.
Yeah, so because this, when there was not galaxies, this was really imprinted in the density of the universe. They're all going to have a preferred distance between them. So this is exaggerated, but somehow statistically, this is imprinted there. There is preferred regions for those galaxies to be, which are the size of this BAO feature. Yeah, this was really imprinted when very early in the universe, and then everything that followed through gravitational attraction in the end followed this distribution. So although it's very homogeneous and isotropic, we can statistically still see those a little bit of preference of clustering around this. And this is a sphere, so that will be a size of the sphere in this direction and a size of the sphere in this direction. And that's what we try to measure. Because you might imagine that as the universe evolves and expands, this sphere evolves and expands. So if I measure the size of this sphere, I'm measuring the expansion of the universe, how much the universe expanded with time. So that's what they measure with DESI. And the definition of this line of sight BAO feature, so you measure this angle here of the line of sight side. It is this RD, which is the size of the horizon when this decoupled. Remember I said there was a time where the photons left, and then there was a time of this sphere. So this is the time when it decoupled in the past. And then this evolved until today, it grow. So this is when it decoupled, divided by the amount of matter in our universe, TM. So this is the matter distance, and this is the definition. And in the same way, I can measure the sphere in this direction, and this is going to be RD divided by the Hubble expansion of the universe, how much the universe expanded. So if you combine those quantities, what I measure directly from DESI, it is this combination RD times H, little h, it is H divided by 100, and omega matter. So I'm measuring the amount of matter in my universe, and I'm measuring how fast the universe expanded from a quantity that I had in the past. So RD is the size in the past, H is how fast it expanded. So DASI measures this directly. Any questions on that?
So you consider only the first peak of this sound wave?
Yeah, you're not measuring exactly a peak here. You're really trying to reconstruct this from the power spectrum. You get the peaks, and then you.
So there is a first peak and some other peaks, but
Yeah, so
first peak is the most important.
no, because you're thinking about the CMB. The CMB is this, right?
That's
not
not
what-
related to actual to the.
No, this is what I measure in the CMB. In the BAO, what I measure, I'm going to measure something like this, a little peak here.
Hmm.
And this is going to give me this distance. But then I'm going to do this in many directions. So it is like a reconstruction measurement of the density. You can really try to think that they're trying to measure this. The
Question is in the 2-point.
It is in the two.
So what are you talking about?
Sorry, yeah, so maybe I can plot the 2-point correlation function. So if you see here is you have KK, here's a power spectrum, and here there is some fixture. They are going to subtract the smoothing, and then they are going to be left only with the peaks. And then you can associate this to those two quantities. Yeah. And the full shape, it is using the full shape, which needs more parameters as well. And again, I'm not an expert on exactly what goes into these measurements, but yeah, in general, that's what they are measuring. Okay, so results. So this is one of their results. So this is omega matter, and this is that RD times H. And there two saw 40% improvement on the precision of those quantities measured. And these quantities that it measures, they can also be measured by the CMB. So even in the DASI results, they say, oh, nothing to be alarmed, but these two values here are 2.3 sigma away from plane. So if you see here in blue is the DASI DR2, and in pink, it is the CMB result. So they're still okay, but you can see that they're a little bit far away. So people are like, still okay, but why? Those are so precise measurements, so why are they not agreeing? But then forget about this, so let's talk about what this result also tells us. And the most exciting result from DASI was the dynamical dark energy. So DASI saw a hint that dark energy is not a cosmological constant, but is actually evolving. Let's unpack what this hint is. And we talked about this a little bit on Friday, sorry to repeat, but this is very important. So what they did to measure the dynamical dark energy, they chose a form for the evolution of the equation of state of dark energy. And this form has two quantities, W0 and WA. So this is just a Taylor expansion in Z around redshift 0. Why they did that? Because this is simpler. This is the simplest possible evolution for the equation of state. So they try to use the data to see if we can see those two parameters, right? If we can see that dark energy is evolving. And here is the result by DASI alone. So DASI alone, it is this dashed 1. And lambda CDM is here in 0 and -1. So we can see that CMB alone, DASI alone does not exclude CMB. So DASI doesn't have the power in the data to exclude. So you can only put a bound on the second parameter. Right? Then let's start combining data, because why do we have this amazing data? So we can combine them. They have different degeneracies. So maybe we can break some degeneracy and also give more power. So then when you combine DASI and CMB, you have the pink line here, which changed a little bit the degeneracy, but also it still allowed omega A0. So basically, It is, yeah.
So let's say, for the BAO, what is the at the decoupling time, what is the Z value?
146 megaparsec.
140 mega.
Yeah,
The decoupling, there must be decoupling time is,
and it is like 1,000 and redshift 1,000.
oh, I see, so similar, so just around the time of the decoupling.
Yes,
I
yes.
see. Then how can we do the linear extension? So
No,
that
because
is
then
the-
you're getting this data and you're getting this quantity and you're evolving until today and you're measuring the size of this ball today.
I see, because the observation data is of today.
Yeah, so you're basically measuring, so this ball was this size at decoupling, and then it is this size now, and this is what DESI is measuring. So from the size today, you're going to measure h of z and omega matter.
I see, that is now, so two
was
or
RD.
something.
Yeah, what?
Z equal to 2 or.
Yeah, from 2 to 0. Yeah. So you're going to see what is the size of this ball 2, and what the size of this ball at 0, because then you see how much it expanded. Yeah. So,
No problem, I misunderstand something. In this plot, so the basic bow seems to, is this dashed red, black dot,
yes,
yeah? And so basically it's very wide.
very wide.
And so if I look at the WA, I see that the maximum value is plus 1.
Yeah.
So there is a typo there. There is W minus 1.34.
It could be that typo here. Yeah.
So it's
It's
plus
hard.
1.
Yes, it is. Yeah, I'm sorry.
It's very wide.
It's very
So
wide.
if they measure time dependence,
Mm.
it means, and they measure omega matter, it means that they measure the transition from matter domination and starting acceleration.
Which, if you measure on the CDM, you also did, right?
Yeah, I know. So I'm just wondering what is the value at Z where it's.
Oh, I'm going to talk about this in one
Okay.
second. 1 second. Just yeah. So I just want you to appreciate here that if you combine with CMB, you still don't have this hint for dynamical dark energy. And if you combine with supernova, which are the others, you still don't have. It is only when we combine that plus CMB plus supernova that then those things go down. And then you have this hint for.
So what is the ingredient that you need to add?
You need to add all of those data sets. You need to add CMB, DESI, CMB, and supernova. If you add only one of those, either.
But it's not important the order. So what is?
No, it doesn't matter. No, you do the analysis with all of them. Yeah. So you need the constraining power of 3 data sets. Each of them that measure a different quantity that then you infer into dark energy. Right? So again, each one of them alone doesn't. So DESI alone does not indicate dynamical dark energy. Only when you combine with data set. That's why we say it's a hint, because there could be something there in this combination of data sets. And this is what this talk is about. So another thing that people thought is that if you look at here, what it's telling us is that not only it is dynamical, but it's phantom, right? So you cross the -1. And then a lot of people think that this might be a feature of using this expansion around the ROM. So this expansion that they use is around z equals 0. And they say, oh, you're trying to use a Taylor expansion in redshift 2. So you're forcing yourself, not the dynamical part, but at least the phantom part. But then they made the expansion in different redshifts, 1, 1.5, and they get the same result.
Seems that from data release 1, the ratio alone is not that WA is not that negative, and the W0 is also starting from positive.
Yeah.
But somehow in the DR2,
Oh, this is a typo. This is plus.
oh, I see,
That's the DR1 and that's the DR2. For that's the alone give the same thing.
I see.
Thank you for helpful.
I see.
Yeah, so that doesn't change with the DR1, the DR2. DR1, DR2 makes those contours a little bit smaller, but it doesn't change the fact that you only get the dynamical dark energy hint when you combine those data sets. And again, here I'm saying not what this means. I'm just saying that, at least for me, since this needs a combination, I call this only a hint. Because I don't know what is going on in those data sets and if I can actually combine them or something. So that is me being careful, but that's how I interpret. Another thing that I find very curious,
Very naively, if there are many data, so then usually we may say that data has some average value and some standard deviation. For different data, how can we get some the combined average value and the combined sigma?
Yeah.
Roughly, is it just usual arithmetic?
No, so if you want to do this the correct way, you really need what we call a covariance matrix, which tells you how those errors in one map to the errors of the other. Because it could be that one sigma here doesn't mean one sigma there, right? So if you are doing things correctly, you have a covariance matrix where you really understand how those two data sets relate. So when you combine those two data sets, there is this matrix in the middle between them that kind of tells you how to combine them correctly. The diagonal of the covariance matrix is 1 divided by the error, and the off diagonals have all the complications of this. The correlations, yeah. So the correlations between the data sets. So this is if you do carefully. A lot of people don't.
We're talking about statistics, right?
We're talking only about statistics, and that is the point of this talk. Yes.
Then of course, systematic errors.
Yeah.
Right.
And that is the
How to
point of
combine systematic errors is another story.
And also some relative weight. So which one should be weighed more or something?
No, but when you combine, when you calculate the combined correlation metrics, you basically sum, you sum one over sigma. So the smaller error dominates.
Always, yeah.
I see.
If you have two experiments, one very weak and one very good, then you error.
Yeah.
So
So if you have two counters like this, I think what is going to say, you have a counter like this. And then you have a second counter like this. The combined one is going to be this, like something smaller. So it's going to win the smaller ones. Okay, so, and that is the point of the talk. Yeah, okay, so this is just that, we're not even discussing. So I just wanted to say this because everybody's saying we discovered dynamical dark energy. I just want you to know, decide for yourself.
So in other words, it's not that DZ is discovering the time-dependent what it seems is that it takes the other results, and is cutting up the tip.
Yeah.
Cutting away the tip of other.
Because the others don't have such a big tip.
Yeah, so if you take the other, if you remove DZ,
Yeah.
these results extend.
Yes, and that's what I was going to say.
You cut the.
Exactly, that's what I was going to say.
What is the reason? So
Yeah.
what is
And that is what everybody's trying to. And why does everything is in a perfect correlation line aligned with 0, right? With lambda CDM.
so
That's very
it's
curious.
not obvious.
It is not obvious. It should not
So
necessarily be the case. So that is where people are now. People are trying to understand what is going on here. Is this okay? So let's go for the other data sets we're talking about. So now we're talking about CMB, and you saw how important it is CMB to the conclusion of the results of DESI, because DESI doesn't measure all the cosmological parameters. DESI measures this too, right? So we need CMB because CMB really gives us all the cosmological parameters. We can really fit the power spectrum of the CMB perfectly and get constraints in all the cosmological parameters. So our hero in cosmology is Planck, which was this satellite that measured the anisotropies in this first light of the universe that we had. But then we have two ground experiments, ACT and SPT, which just released results this year. And let's first talk about ACT. So ACT is a really nice experiment. So ACT is what they say, the biggest amount of data we had since Planck. So this really increased the amount of data as much as we increased the data when we had Planck. This data has 5 times more resolution than Planck. It is 1/3 of the Planck noise. It also allows you to see the small scales because it has so much resolution that it can really actually see clusters of galaxies with the CMB map. And it has something that the Planck didn't have, a much more precise polarization measurement. So now we not only have the temperature for the CMB, we have the polarization of it. And this DR6 is the biggest data improvement since Planck. So it is huge. Here, just so you understand, here is the TT power spectrum. So the temperature 2-point correlation functions of the map. So Planck, it is in yellow, and ACT is in blue. And you can see just by eye how better it is, how smaller the error bars are. You can also see how ACT extends to smaller scales. So large L is small scale.
So they up to 500, they superimpose.
Yes. So they don't have the beginning of the power spectrum because they only have a fraction of the sky. So ACT is ground-based, so it's only 30% of the sky.
What about
I play a lot with the likelihood. This likelihood has so many things that it has to fit. It has to fit not only the foregrounds, it has to understand the atmosphere well.
Yeah, so in other words, I guess that there are many more uncertainties.
But also they have more channels. Yeah, they claim that they understand that and they have a lot of channels to really understand the absorptions and everything.
Very motivation. You don't put a detector on a telescope.
Also, you're in the Atacama Desert, which is much drier and very high altitude. So they try to minimize all that. And also they have a very large, it took them like years to calibrate.
So I just wondered, in your talk on Friday, you insisted on, on these additional parameters.
And I'm going to
so I'm just wondering if compared to Planck, ACT has many more.
Yeah, and it has many more. Exactly. They have partial sky. They have everything bad that can happen between us and our measurement, right? Between the atmosphere and everything, although they try to minimize that. Yes, so they have many.
That's a very stupid question because, you know, the motivation in the first place to put the telescope on, so put a telescope on a satellite, like in Planck, it's extremely expensive.
Yes,
it was extreme, was because you didn't want to have absorption from the atmosphere.
Yeah.
So what has ACT better than the previous generation of detectors? In other words, it would have been cheaper to go, instead of putting a detector on a satellite, which is extremely more expensive and risky, to do that from ground.
Yeah.
So I would have thought that the data from a ground telescope on the CMB would have been anyway poorer. That's why.
If we had done ACT at the time of Planck, I think it would have been a very bad result because we didn't have as good detectors or as the good understanding as we had. So we really needed a space mission. Of course, we wanted ACT to be a space mission instead of being a ground-based mission, but you cannot get the money for that. We cannot get the money for CMB.
In other words, well, since we were talking about how to combine systematics can be in understanding the absorption.
Which is- Yeah, which is what they claim they understand really well, and they have hundreds of papers on how much they tested the atmosphere with calibration sources and different things, comparison to Planck and everything. So yeah, indeed, it is always better to go to space. But one funny thing, so when Planck was finally released, the technology of detectors were 10 times better already, because those things take time.
Yeah.
Right? So I'm seeing this in Lightbird. I'm part of Lightbird. So Lightbird will be launched in 2030. We're following the plan from 10 years ago. So detectors are designed 10 years ago for something that is going to fly in the 2030. So yeah, there was so much advancement there. And then that is ACT. ACT is a lot of advancements on understanding of the detector and everything.
What about the error bars, the errors? So here, usually you claim that for Planck, the error bars are so small that you
Yeah.
never see it. And what about this?
Yeah, so these are even higher, right? Yeah. So this is the blue one.
Where is the CT? So is,
Blue.
is this range here?
So ACT can really go to smaller scales because you have better resolution, so you can resolve smaller structures. Yeah. Again, this is the final result, error bar. Taking into consideration all of the, I'm excluding the atmosphere, I'm excluding synchrotron, dust, blah, blah, blah. I'm doing the full analysis on that. Yeah.
In other words, what is ACT really doing good for compared to Planck is that when Planck is losing sensitivity
Yeah,
at small scale,
they pick it up.
it can be that
Yeah.
is responsible for.
And also, they pick it up in EE, right, in polarization. So here's the EE per spectrum. Planck did not have this. And look how beautiful it is. Yeah. So there, it's like almost the first measurement of polarization we have, right? Yeah. Just to show you T. So this is the cross correlation between temperature and E. And yeah, it's a bigger improvement. And then it extends to smaller scales. And here I'm only plotting until 4,000, but they go to 9,000.
Sorry?
They go to 9,000 in L. Yeah, but then it's a choice of you how much you're using.
If it goes 9,000, then a little bit bothering me is that you said the uncertainties, the resolution is about the arc minute, right?
Yeah, that's what it said.
Not arc second.
It's 1 to 2 arc minute resolution.
So not arc second.
I don't know, to be honest.
Because I mean the 1 degree, so L equal to about
Okay.
100 is a 1 degree.
Mhm.
And by multiplying 60 is about a 5 or 6,000. That should be already arc minute size.
Mhm.
But
I know
going
that-
to 9,000 is so below that. So
Yeah.
because I mean the active the optics
Mhm.
that we really
Yeah.
correct all the air changes, reflection index changes.
Yeah,
So they say that, if I remember correctly, they say that they can make the resolution up to arc second.
it could be that they don't use that for cosmology. Because I know that there's a lot of cluster physics now being done with ACT. So they can actually resolve clusters, they can resolve globular clusters. It's impressive. I don't have here, but I had some maps of him.
So sorry, I didn't understand your question. You're saying that since they extend to 9,000.
Yeah,
means
then
that-
compared to the 1 degree, which corresponds to L equal to about 100. It seems to be about 90 times the times, and from arcs 1 degree to arc minute is 60, factor of 60, right?
I think it's like where they have this improvement in resolution, it's probably until arc minute, but then they can extend and study other
If you say
things.
that they go up to 9,000.
They do,
That's
yeah.
what I mean.
And I know that there's some people doing cluster physics, doing SE, synapse Dodge effect. But at least in the data analysis I used, I don't use until 9,000. And they also, I think we stopped in 6,000 or 5,000, yeah. So, yeah, so I just wanted to show,
I see, so I
How
record
better?
9,000 correspond to cluster,
I think
yellow
so.
cluster scale.
Yeah. And they cannot push smaller than that. That's what they told me. So cluster
So
scale,
that's the limit of X.
yes. Yeah. They have a beautiful list of clusters that they can actually measure the properties with ACT. And there's a lot of people now doing small scale physics with CMB, which is, I could never believe you could do that. Okay, so all of that to show you the beautiful results from ACT. So first, to test the lambda CDM, right? And to test the concordance with Planck, because that's important, right? Planck is full sky, so it has to agree with Planck. So here I show ACT and Planck for some of the cosmological parameters, and we can see that they agree with 1.6 sigma among each other.
But X has a lower H0.
Oh my God, you notice, yeah. Those are the things I wanted to shock you with, and yeah. So it has a smaller, even smaller H.
So worsen the tangent is more serious.
Yeah. It is bigger error bar, so it's compatible. So you cannot say that, right?
Nice.
Yeah, but the central value is shifted. Yeah.
The other hand, NS is always.
Yeah, NS we're going to we're going to discuss a lot. And also they also tested extensions of lambda CDM. They actually tested 30 extensions of lambda CDM. And all of them are not preferred with respect to lambda CDM, including the early dark energy as we saw last week. So they did an amazing job.
So it means that the chi-square over the number of degrees of
Yeah.
freedom is of the lambda CDM is best.
Yeah.
compared to-
Yeah, and they not only did like reduce chi-square, they did many other Bayesian, and so they tried like many metrics. And with all of those metrics, lambda CDM is a better fit to ACT data than any extension. Right, then there's SPT that I'm going to speak really quickly because it's less powerful. So we had this year the 3G first release, and this is 4 to 10% of the sky, so it's really small sky. This first release is like 5%, so it's not a lot. And it's also very high quality data. And here's just a summary, Planck, ACT, and SPT. As you can see, this is SPT paper, so they claim they have a smaller error bar than ACT. I don't know if that's true. I'm not in SPT, but it's impressive seeing here. But what it shows is that they are all better than Planck and all they extend to smaller scales than Planck. I think that's all we need to see here. And here are their constraints. And again, there's a amazing concordance with Planck and also with ACT. So all cosmological parameters are within 1.5 or 1.6 sigma from each other. So all of that to say that all of these ground-based telescopes, although they have a much more complicated physics that you have to understand from the atmosphere and all, they have very good results, very precise results with great agreement with Planck. So what is the next obvious step? I measure something with ACT, it agrees with Planck, so we're safe. So let's combine those data sets. So that is the next obvious step, right? So when we combine data sets from those ground-based CMB and also large-scale structure and also Planck, we have this. So here is Planck alone, Planck plus ACT, Planck plus ACT plus lensing plus DESI. So the one combining with everything is this one. And we see that they are all in agreement, right? So that is the story until so far. But there's actually a discrepancy. They just didn't plot the correct quantities. So if you plot the results from ACT and SPT for the parameters from DESI, from BAO, which is omega matter and RDH, we actually see that ACT here in blue and DESI in gray, they are actually very shifted from each other. So both are measuring the BAO, right? So CMB measures the acoustic peaks. This is the BAO. I'm measuring the BAO also directly. It's a bit inferred in all the cosmological parameters, but I'm measuring the BAO. Versus DESI, there is a discrepancy here. When I include SPT, there is also a discrepancy, although there are bars a little bit bigger. This is called by some people, by us, we call this BAO-CMB tension. Some people call it omega matter tension, because this also appears in weak cleansing data like DS, KITS, and HSD. And here we can see from the SPT data, we both published this at the same time. We discovered this at the same time. We have something from a 2 to 4 sigma tension between BAO and CMB data set. So if you combine SPT and ACT, this is like 3.7 sigma. So this is a very strong discrepancy, right? Something is more than 3 sigma away from each other, those quantities, to the point that if you look at this at SPT paper, they don't even combine with DESI. They say those data sets are discrepant. I cannot combine them because they go above the threshold of 3 sigma away from each other. So SPT never publishes their results like ACT does. ACT does Planck, ACT plus DESI. SPT doesn't, because they claim that this discrepancy, it's so big that it goes above the threshold to say that those 2 data sets are compatible. They are not anymore. They are incompatible, so they cannot be combined. So caution is required when you're combining data sets. And you see that when we show this, we did not see it, right?
Yeah, in one hand, Planck, ACT, and SPT, they are all measuring the CMB.
Yes.
While DESI is the large scale structure.
Yes.
So it seems that they are looking at the different, even though theoretically, from the theory point of view, it should be related.
Yeah, if it was a lambda CDM model,
Right.
and if all the systematics of both sides are under control, it should be the same thing. So one of those things is wrong.
If the theory is
Either the theory is wrong,
yeah. Right.
and they know what they're doing, or the systematic.
Counting photons is not the same thing.
I'm sorry.
Counting galaxies, counting photons.
That's right. That's
But we
right.
do all the transformations so they can be the same thing. So some
Well,
people,
you're using a moment. You're using a moment.
yeah, so
And also we do need theory. So theory says the same BAO, right? Or from the LSS and the BAO from the
The errors, the systematics are different.
So I don't think in the theory of like a measuring BAO here and BAO there is an error. We have been doing BAO for many years and comparing with CMB. And there is much more complexity in the data. That there is. DESI measures those spectrum with such complexity that it could be that I don't understand those galaxies.
No, but what I want to ask is that you are testing structure formation, because in the CMB you measure a universe that is still completely is uniform and isotropic at 10 to minus 5. When you count galaxies, the universe is no longer isotropic. It means that there was an evolution, right?
Yeah.
You formed some galaxies.
Yeah.
And for instance, we know that we need omega matter. Indeed, in particular, we need dark matter. Without dark matter, you don't form galaxies because the photons decouple too late. In other words, it's model dependent.
It is everything.
Yeah, of course,
all
you
I'm
are
saying is lambda CDM.
You are testing the lambda CDM.
You're testing the lambda. All of this is in the context of lambda.
Yeah. So if you believe in lambda CDM,
Yeah.
there is this tension. Yeah.
Exactly. So that's what I want to say. If you believe in lambda CDM and you believe in the systematics or errors that they put, the way they constructed their data sets, which, let's be honest, those are very competent groups, but it's a very hard thing to do. Like there's the atmosphere, there's the galaxies, you see how many tracers they have in DESI, right? Does it mean that this galaxy and that galaxy are in the same way? They claim that they are under control. They tested, but so there's something here. I just want to say that there is this tension that they don't claim but only us and the SPT team claimed. Because we were looking at the right quantities to see this tension. And this is serious because it has implication to the other cosmological parameters that we're inferring. They are the ones that we want, right, to infer.
So just to understand, if we interpret this discrepancy in terms of omega m, the data from ACT requires more omega m, more density.
Yeah.
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 So does it mean that they observe more power in those scale? So they need to form structures faster compared to, in other words, because the data from, if I understood correctly, is ACT is measuring, has a very good resolution, so it has data at large angles, so at small scales.
Yeah.
And so it has if you do not consider that data, the error bars are very large, we don't say anything.
If
For
you don't
instance, the
consider
Planck data cannot reach that.
no, you can, yeah.
But now you have this data,
Yeah.
and from this data you are measuring the power at small,
Yeah, in all scales, including the small.
in only the small ones. And so if you require, you need more matter, it seems that you are observing more power at small scales than you would expect. Just extrapolating the data from the CMB or Planck, this is the.
It could be one interpretation, but then
No, I'm just asking if it's possible.
No,
It's an easy way to understand.
it is one way, but in the end, both of these results need to be correct. So if you put a model that requires more dark matter and then you analyze that with this, it's not going to work. And I can tell you this appears for other data sets of large scale structures. So. Yeah, so new physics is what, again, we're not in the collaborations. We cannot play with the systematics, right? What can we play? We can play with new physics, right? But this talk is not about that. This talk is just to show you this, because not a lot of people have noticed that, but us in the SPT collaboration have noticed that. And now this is, like you said, this is all over the place. So in this talk, I'm going to talk a little bit more about one of the consequences of that. So the shifting those two parameters has a consequence in shifting a bunch of other parameters, including the spectral index NS, which is something we thought we measured well and we knew well. So again, here I'm showing omega matter and RDH, but I'm also showing you NS. And here I'm only showing you ACT, Planck, and DESI. So as we see here, here is another way of seeing that the tension, right? So Planck sits in the middle, DESI is here, and ACT is here. Again, here for RDH, Planck sits in the middle of everything. I don't know why, I don't know what's going on. If you measure then an S from Planck and ACT, they are in, they agree, right? And this pink band, it is the usual values of NS for the most accepted inflationary models from Planck. So Planck and ACT agree, although there is this tension with that. So then we combine, yeah. So then when we see, we illustrate in this plot a little bit better this dependence on NS. So here's omega matter, here's some combination like RDH, here's DESI data, here's ACT data. And it's funny that we see that there is only a tiny overlap between those data sets, right? And where it overlaps is usually for large values of NS. So this is just like the points of the MCMC chain, right? So this already tells us what we're going to find if we combine these data sets. Oh, sorry. So if we combine ACT and DESI, this is actually going to push NS to larger values because again, here, they only overlap with larger values. And this is going to push NS to larger values. So just so you can see in values, so ACT alone, which was in agreement with Planck, gives you 0.966, and ACT plus DESI gives you almost 0.98. So this is a 3.34 sigma discrepancy from the values of NS. So this is a highly significant shift in the value of NS. And then if you're wondering, oh, it doesn't shift so much, it is because this is almost the same data set. You're just adding a data set. So this shift, it is 99% not probable to happen. This is what this 3.34 sigma means. It should not happen. The shift with Planck, it is 1.5 sigma with respect to DESI, and with respect to ACT, it's 3.34. If you do SPT, SPT also gives very small values of NS. SPT is the yellow one here. So I think the NS values from SPT is 94 alone. But then if you combine with DESI, this goes to 98 again. But again, DESI is very imprecise. So what you have been hearing in the literature that, oh, NS from ACT is large. A lot of people have been saying that, oh, let's review all of our inflationary models. It is only large when you combine with DESI. ACT alone actually gives you a smaller value than Planck. So this is a consequence for. And the explanation we think it's happening, it is because the way we measure NS, it is kind of indirect. Let's think matter about omega matter. So the way we measure omega matter, it is actually the relation between the second and third peak here. And Planck has all the peaks, while ACT only starts here in the middle of the second peak. So we believe that when I combine DESI with ACT, everything shifts towards DESI, because ACT allows you a little bit more freedom in these first two peaks on the fit of this. So it allows you to change omega matter a little bit more than Planck allows.
In other words, CT has less information about
omega. That's what I think is happening. But again, I'm not from the. So that's why I think when you combine with DESI, the tension is there, right? When I combine with DESI, this shifts, because with Planck, if I combine Planck with DESI, it doesn't shift things too much, because Planck has a very strong measurement of omega matter. So they're there. They are in 2 sigma tension, but I can combine Planck with DESI and not cause this huge shift. While if I combine ACT and Planck, I see a huge shift. And we think it's because of this region here. To be decided, I don't know. And this has huge impacts on inflationary models, because as we saw, NS is a discriminator of inflationary models. And from Planck, our lesson was like, there's no viable targets for NS bigger than 96. The viable targets, because we are in this region, right? So, sorry, this is 7. It are those ones. But again, to make those ones become larger, you would have to change something, like change reheating or change some condition in those models. And unfortunately, those models are very resistant to those changes. So if you change the number of V-folds, if you change reheating and all, they only change a little bit, not enough to explain that value. So if we take at face value, this large value of NS, which I'm going to say again, we don't know what is the value of NS, right? We're noticing a tension. So we don't know who is right at this point. If we took this at face value, this means that we need to find new models, which are the preferred ones. And those are models with NS bigger than 97. And those are other models. Instead of having purely like preference for exponential potentials, we would have a preference for maybe polynomial potentials from now on. So this has a huge impact. So we really need to understand what is going on. So I think what I want to say is, like, one thing we know for sure is there is this tension between ACT and SPT and DESI. Planck, we wouldn't call attention, but it's still 2 sigma away from DESI. So there is a shift. This can impact NS. But the thing is that at this point, we don't know. We don't know what is the correct value of NS. It is the Planck one, it is the DESI one, or is the ACT one. We don't know. So with this, I leave my conclusions. But if you allow me 1 minute, I have other consequences of this. So other possible consequences of this tension. So there are many. So as has been studied in the literature a bit, this can affect the sum of neutrino masses that infer from DESI. This can impact the value of megamatter. This can give you a presence of curvature that might not be there. It's just from the tension, or even dynamical dark energy. So for example, dynamical dark energy. You only really have the combination when you combine with CMB, right? If this is 2 to 4 sigma away from each other, this can be driving this preference for dynamical dark energy. And there's a few papers already on that since we published our paper. So some people say dynamical dark energy solves the tension. This was the new physics necessary to solve the tension. Other people say this is a feature of 2 data sets that are discrepant. So this is, we shouldn't combine them until we understand. So I don't know which one is correct. So another one is neutrino mass. So there is since we measure the neutrino in the border, we usually say that the posterior is peaking in negative values. And some people, I think we've all seen the paper saying explanations for the negative neutrino mass, right? I don't think that is happening. This is just like we don't have enough data. But there's a few papers saying that actually what is wrong, it is this tension and also the value of tau. If I had a different value of tau, this would actually shift my neutrino constraint to positive values. So it's actually like a lack of knowledge in tau. Oh, sorry, optical depth. Yeah.
Well, because one of the neutrinos is tau.
I'm so sorry. Yes, particle resistance. I should remember. Yeah. So you can see here. So if you just change tau from 0.06 to 0.09, you shift those things into this degeneracy line into positive. But again, remember, low L E mode polarization fixes tau really well. So if ACT is correct, ACT can fix tau. If Planck is correct, it can fix tau. But since we don't know if they're correct now, also curvature can explain this tension and so on. So I just want to say that there is a BAO-CMB tension. Okay, I think this is there. The reason we don't know, it could be systematic, it could be new physics. There's a lot of papers in the market explaining this with new physics. And I don't know if this is an explanation for the tension, or the tension tells us you should not use those data sets to explain something like dynamical dark energy. I don't know what is the answer. So this talk was just to present you this puzzle that it isn't solved, and I don't know what to do now. And hopefully all of you know the puzzle now. So thank you.